Welcome to Databricks Certified Machine Learning Professional Exam Preparation. In this podcast, we'll explore key topics, practical concepts, and examples to help you prepare confidently for the exam. Today, we're taking a deep dive into machine learning operations, or MLOps. This is a really critical area for the certification, so let's get started.
Absolutely. MLOps is no longer just a nice to have. It's really the bedrock of any successful machine learning deployment. Think of it as bringing the same kind of robust engineering practices we see in software development, but to the entire lifecycle of an ML model.
Okay, let's unpack this then. Our goal today is to really understand the core ideas behind MLOps, break down its key parts like data ops, model ops, DevOps, and see the real advantages it brings. We'll also be focusing on how Databricks tools specifically support MLOps, drawing from that advanced machine learning operations source material. And importantly, we'll weave in practical examples, stuff that's very similar to what you might actually see in the exam.
Exactly. We want to go beyond just the definitions, give you a concrete feel for how these MLOps concepts actually play out, especially within the Databricks environment.
Right. So let's lay the groundwork first. MLOps fundamentals. What's the essence of it all?
Well, at its heart, MLOps is really the coming together of DevOps, data ops, and model ops. If you look at the visual in the source, it shows it as where these three disciplines meet. It lets us effectively manage the three vital parts of any modern ML project: the models themselves, the data that feeds them, and the code that defines them. It's about having a unified way to manage and govern these key assets.
A holistic approach then. Models, data, code. So what's the big win here? Why should someone doing ML really care about adopting MLOps?
Oh, the advantages are pretty substantial. First off, efficiency. You get higher quality models in less time because you're streamlining workflows, automating things. Second, scalability. It makes managing, potentially thousands of models in production actually feasible. And maybe most importantly, it seriously reduces risk. You get repeatable workflows, automated monitoring. It brings transparency to the whole ML process.
Efficiency, scalability, lower risk. Yeah, those are compelling. The material also talks about how MLOps helps ensure data quality. How does it do that?
MLOps really builds data quality in right from the start. This means optimizing the data processing pipelines, making sure data is handled correctly all the way through. It also centralizes how you discover, manage, and govern data. Makes it easier to find, understand, and control your data assets. Plus, you get clear data lineage and continuous monitoring, so you always know where your data came from and can spot issues fast. And honestly, just fostering better collaboration between the data science, engineering, and ops teams helps improve data quality overall.
Makes perfect sense. And I see this principle highlighted, treating machine learning as code. Why is that view so important?
Yeah, that's fundamental. It's about bringing that software engineering, reliability, and rigor into the ML world. It means automating CI/CD, continuous integration, and continuous deployment pipelines, specifically for your ML code. This lets you do continuous code testing to catch bugs early, use version control properly for everything, and set up robust production-ready workflows with real orchestration and automation. Basically, moving away from those manual, often error-prone ways of doing things.
So it's not just about the final trained model file anymore, is it? We're talking about the whole package.
Exactly right. MLOps pushes us to think beyond just the model as a static object. The model code, the scripts for training, pre-processing, evaluation, that software, needs the same discipline. And the trained models themselves, they become data artifacts. They need versioning, lineage tracking, performance metrics, managed through their entire life cycle, including monitoring once they're out in the wild.
All right, good handle on the fundamentals now. Let's move to the practical side. What are the key components of MLOps, and which bits of the ML process can we actually automate?
Okay, so the source lays out a pretty clear sequence, and yeah, many parts are prime candidates for automation. It starts with defining the business problem and success criteria. Now, this initial bit needs human input, obviously, but those criteria, they directly feed into the automated model evaluation later on. Then you've got data collection and exploratory data analysis, EDA. While EDA is often interactive, the data collection pipelines themselves, those can and definitely should be automated for consistent data flow.
Right, automated getting the data in. Makes sense. What comes next?
After collection and EDA, you have data preparation and feature engineering. This stage is a huge target for automation. You codify your transformations, your feature creation steps, ensures consistency, reproducibility. Then, model training and tuning. The source specifically calls out automated model retraining that's crucial for MLOps. Plus, automating things like hyperparameter tuning helps you find the best model configurations efficiently.
Automated retraining definitely sounds key for keeping models relevant. What about after training?
Post-training, we hit model evaluation, review, and governance. Now, human oversight is often needed here, but the core evaluation calculating metrics, comparing against baselines that can be fully automated. Then there's model deployment, inference, and serving. Automating deployment means you get models out quickly and consistently across different environments, like staging and production. And finally, model monitoring. Absolutely vital, and again, automation is key. You're continuously tracking inference tables, inputs, predictions, watching data quality, model performance, detecting drift.
Okay, that paints a picture of a highly automated, well-managed lifecycle. Now, the source talks about the benefits of a unified platform like Databricks for MLOps. What makes that so helpful?
Yeah, a unified platform like Databricks really simplifies things. It brings DevOps, DataOps, and ModelOps practices together in one place. This tight integration makes collaboration much smoother between data scientists, data engineers, ops folks. Everyone's working on the same platform. It also streamlines data management's central place to store, process, govern your data. Ultimately, it breaks down those silos that often pop up between different functions, leading to a more cohesive, data-centric approach to ML.
So less context switching between different tools and systems.
Precisely. And Databricks has a whole suite of tools built for MLOps. For instance, Databricks Workflows lets you schedule data pipelines, automate general workflows, and specifically ML workflows. You can use job parameters, dynamic values, even pass values between tasks. Very flexible for automating complex stuff.
Workflows sound powerful for orchestration. What other MLOps tools does Databricks bring to the table?
Well, for EDA, dashboards, general coding, you've got Databricks SQL, dashboards, and of course, the notebooks we all know. The Databricks Feature Store is super valuable for creating, storing, managing, discovering features, promotes reuse, consistency. Then there's ML flow model tracking for the whole model development lifecycle. You've also got Lakehouse monitoring integrated with ML flow for that comprehensive model monitoring of performance, health, drift detection. Even for no-code model development, there's Databricks Auto ML. And for version control and sharing your model code, Databricks Git folders integrate smoothly with Git.
It definitely sounds like they're aiming for a very integrated MLOps experience there.
Yeah.
Okay, let's talk about separating environments. Dev, staging, prod. The source mentions two main ways to do this in Databricks. What are they?
Right. The first strategy is using completely separate Databricks workspaces for each environment. One for dev, one for staging, one for prod. The upside here is simplicity within each environment, better security isolation, easier tracking. It minimizes the risk of, dev stuff accidentally impacting prod. Scales well, too. The downside, potentially more administrative work managing multiple workspaces and maybe higher costs since you have separate resources for each.
Okay, so isolation versus admin overhead and cost. What's the alternative?
The other way is using a single Databricks workspace but enforcing separation logically. Using naming conventions, access controls, maybe different folders or projects inside the one workspace. This can mean simpler overall infrastructure, potentially lower cost because you're sharing resources, and maybe easier collaboration in some ways. But it might not scale as well for lots of independent projects. Those logical environments can get complex to manage, and you have to be really diligent with policies to keep things separate. Security can be trickier too.
Yeah, definite trade-off there between physical isolation and shared resource management. Okay, shifting focus a bit. The source outlines some MLOps guiding principles for optimizing how we develop and deploy models. What are the key ones?
Several big ones stand out. First, the absolute importance of automated and orchestrated CI/CD pipelines. Setting these up to automate as much of the ML lifecycle as possible, build, test, deploy, reduces manual errors, ensures consistency. Breaking down big ML workflows into smaller, manageable modules really helps here.
Automation, again, seems like the core theme. Yeah. What else?
Absolutely. Another key principle is comprehensive automated testing, a solid strategy covering unit tests, integration tests, end-to-end tests, maybe even more advanced stuff like canary or blue-green deployments built into your CI/CD. Then, continuous monitoring and alerts are essential. Keep watching model performance, infrastructure health, use dashboards, metrics, get actionable insights. Automated alerts are crucial for catching issues early. And finally, building ML assets as code, using infrastructure as code, or IAC, and templates to standardize and automate how you create and manage your ML infrastructure and components. Brings consistency, repeatability, version control to your setup.
These principles really highlight that engineering discipline MLOps brings. Let's go a bit deeper on the continuous workflows, CI, CT, CD, CM. Can you break those down in the MLOps context?
Sure, they're really the heart of modern MLOps. Continuous integration, CI, builds on traditional CI. It automatically triggers pipelines when code is committed. But for ML, it also runs tests on data schemas, maybe even baseline model performance, not just the code. Everything's tracked in version control. Goal is to integrate changes often and catch issues early.
Catch problems early when they're cheaper to fix.
Right.
What about continuous training, CT?
CT is all about the models. It's automating the retraining process, maybe on a schedule, maybe when new data arrives, or maybe when production performance dips. CT also covers automatically logging all the training experiments, metrics, making sure everything's reproducible, automating hyperparameter tuning fits here too, and rigorously evaluating retrained models before they move on.
Keeping models fresh and optimal through automation. Okay, now continuous delivery or continuous deployment, both often just call it CD. What's the difference for MLOps?
Good question. They both deal with releasing and deploying ML assets. Both involve automatically validating models in, say, a staging environment after they pass CI and CT. The key difference is that final step. With continuous delivery, the validated model is ready for production, but a human needs to explicitly approve the deployment. Continuous deployment goes all the way. If the model passes all the automated checks in staging, boom, it's automatically pushed to production. No manual gate.
Manual gate for delivery, fully auto for deployment. Got it. And finally, continuous monitoring, CM.
CM is about keeping watch on models after they're deployed in production, continuously tracking performance metrics, accuracy, latency, whatever matters. Also detecting drift changes in input data distributions or model predictions over time. Based on predefined rules or thresholds, CM systems can then trigger actions like automatically kicking off a retraining pipeline or sending alerts to the ops team if something looks off.
So it's a full feedback loop. Build, train, test, release, deploy, predict, and then continuously observe and react. The source also gives some examples of CI/CD pipelines and MLOps. Can you highlight a couple?
Yeah, definitely. For CI, you might have a code testing and integration pipeline runs unit integration tests on code commits, ensures merges work. Or a data pipeline validation pipeline checks data integrity, schemas when pipelines change. A similar one for feature engineering validation, maybe an automated security and compliance testing pipeline. For CD, you could have a model validation pipeline, runs tests, compliance checks on a new model, a deployment to staging pipeline, a staging validation pipeline doing more thorough E2E and performance tests there, and finally, maybe a model registry and promotion pipeline that manages registering models and moving them through stages like staging to production after successful validation.
Those examples really help see how the whole lifecycle breaks down into automated steps. And what are the main Databricks tools we'd use to build these CI/CD, CDCM processes?
Databricks offers a strong set of tools for this. We mentioned Databricks workflows and jobs. They're central for scheduling and orchestrating pipelines. Delta Live Tables, DLT, are great for building reliable ETL pipelines, ensuring good data quality for training and inference. Managed ML Flow is your hub for tracking experiments, versioning models, automating deployment. And Databricks Git folders give you that seamless Git integration for version control and collaboration on your code and notebooks, which is fundamental for CI/CD. They're all designed to work together.
Okay, let's pivot to testing. Super important in MLOps, especially in CI/CD. The source mentions the testing pyramid. Can you explain that?
Yeah, the testing pyramid is a great mental model. It suggests how to balance your tests. At the wide base, you have lots of small, fast unit tests. They check individual functions or components in isolation using small data. Quick to run them often during development. In the middle, fewer integration tests. These check how different modules work together. Testing business logic, maybe with slightly larger data, usually run in CI. At the narrow top, you have even fewer end-to-end E2E tests. These simulate full user workflows, testing the entire system with production-like data and environments. They're comprehensive, but slower and more resource-intensive. The idea is to catch most bugs early with the faster, cheaper unit and integration tests, but still have those E2E tests for overall system validation.
Wide base of fast tests, tapering up to fewer, slower, but more comprehensive ones.
Right.
The source also talks about organizing functions and unit tests within Databricks notebooks. What are the options?
There are a few ways people do it. One way is to write your functions and unit tests completely outside notebooks in separate Python or Scala files. Good for reusability, lets you use full testing frameworks, but maybe not ideal for Scala notebooks right now, and it's more files to manage. Another way, define functions in one notebook, write tests for them in a separate test notebook. Clear separation still allows reuse via %run, but again, more notebooks. Or keep functions and their tests in the same notebook. Can be easier initially, simple to track tests for functions, but makes reuse harder and might get messy for complex projects.
Different trade-offs for organization, reuse, complexity. How do you actually run tests in notebooks? What tools?
You can use the %run magic command to execute another notebook, like importing functions into a test notebook. Then you write your test functions or classes using standard testing frameworks right there in the test notebook. For Python, popular ones are unit test and pytest. R has test that, Scala has Scala test. Even for SQL, you can just write assert statements. These frameworks give you structure for defining tests, checking results, and reporting.
Good to know we can use standard frameworks within notebooks. What kinds of things should we be testing in an ML context? Any examples of test functions?
Oh, yeah, lots. You definitely want tests for data quality checking for unexpected nulls, correct data types. Tests for your data transformations, like normalization or scaling, do they produce the right range, handle edge cases? For training code, maybe test that your loss function calculates correctly or that evaluation metrics compute as expected. And for deployed models, integration tests checking the API endpoint, does it respond correctly to sample inputs?
All critical checks. The source also gives tips for reducing testing time and cost. What are some strategies there?
Yeah, you don't always need to run tests on the full data set or train for ages. Using smaller data subsets for unit and integration tests is common much faster. Reducing training iterations or model complexity during testing helps too. For integration tests with external services, using mocks or stubs can speed things up and make tests more reliable. And maybe limit load testing initially to find big bottlenecks before scaling up. The goal is efficiency, catch common issues quickly without breaking the bank on every test run.
Targeted testing, smaller data, simulations, efficiency makes sense. Now, E2E tests are flagged as crucial for ensuring operational separation between environments. Why are they so important for that?
E2E tests are vital here because they test the whole system working together across environments. By simulating real data flows from start to finish, they can catch configuration issues, integration problems between dev staging prod that unit or integration tests miss. Specifically for environment separation, E2E tests help confirm that a model validated in staging behaves correctly in production, without weird side effects or data leaking between environments. They validate the whole deployment workflow is isolated properly.
Making sure what works in staging actually works safely in prod without interference.
So,
Yeah, okay. The source also mentions detecting and rolling back issues, using canary deployments as an example. How do canaries help with rollback?
canary deployments are where you roll out a new model version to just a small slice of production traffic, the canary group. You monitor this group closely, comparing its performance to the main group using the old model. If the canary shows problems because it's only affecting a few users, you can quickly pull it back, roll back to the stable version before it causes widespread issues. It's a low-risk way to test in production.
Controlled rollout, limited blast radius, easy rollback. Got it. Lastly, on testing, Spark-specific testing. What's unique about testing Spark apps?
Well, Spark's distributed nature adds complexity. You need to test Spark APIs correctly. Data frames, datasets, streaming, MLlib often require special assertions for comparing data frames dealing with row order, approximate flow to quality, nulls. Testing UDFs, user-defined functions, in a distributed setting needs care. Generating realistic test data, maybe emulating external dependencies like Kafka, and testing notebook code specifically are all things to consider with Spark.
Right, testing the logic in its interaction with distributed Spark. What testing libraries help with Spark?
Spark has some built-in testing utilities. There's also Spark testing base for Scala, and Python helps test RDDs, data frames, streaming. Spark Fast Tests and its Python version Chispa are designed for faster tests on Spark 2 and 3. And PyTest Spark integrates Spark testing nicely with the popular PyTest framework in Python, so there are good tools available.
Good range of tools indeed. Okay, let's switch gears to model rollout and monitoring. A/B testing was mentioned briefly. How is that used for rolling out new models?
A/B testing is a really important rollout strategy. You deploy your new model, let's call it B, to a random subset of users or traffic. The rest continue getting the old model, A. Then you compare key business metrics, conversions, clicks, whatever matters between Group A and Group B. By analyzing the results statistically, you can see if Model B is actually performing better in the real world before you commit to rolling it out to everyone. It's data-driven validation.
Data-driven comparison on live traffic. Makes sense. Now, Lakehouse monitoring. What is it, and what are its main benefits?
Lakehouse monitoring is Databricks' integrated solution for tracking the quality of both your data in Delta Lake and your ML models. It uses Unity Catalog metadata to automatically profile and monitor things across your whole lakehouse. Key benefits: you can monitor all kinds of tables: bronze, silver, gold, time series, inference tables, features, all in one place. It does automated data profiling, detects model drift and performance issues. It's a managed service, so simpler operations. Gives you real-time alerts, auto-generates dashboards, and critically, the monitoring results themselves are stored in open Delta tables, so you can analyze them further or plug other tools in.
Centralized automated monitoring for data and models. How does it work under the hood?
It runs as a scheduled background service. It incrementally processes data in your monitored Unity Catalog Delta tables. It calculates profile metrics, automatically null counts, distinct values, mean, median, quantiles for numbers, frequencies for categories, stores these in monitoring tables. For drift, it compares the current data distribution to a baseline you define, maybe a previous time window or version. For model performance, if you provide the ground truth labels in your inference tables, it calculates quality metrics like accuracy or MSE. You can also define your own custom SQL metrics for anything specific you need to track.
So it's constantly analyzing and storing metrics. What kinds of specific metrics can we track?
A wide range. For table fields, null percentages, min-max AVG, distinct counts, distributions. For models, if you provide labels. Standard stuff like accuracy, precision, recall, F1 for classification, MSE, RMSE for regression. And as we said, custom SQL metrics let you track pretty much anything you can calculate from your data business KPIs, specific data quality checks, you name it.
Custom metrics sound very flexible. How do we actually interact with Lakehouse monitoring in Databricks? What's the UI experience?
You mainly use the Unity Catalog Data Explorer. That's where you configure monitoring for your tables, choose metrics, set alert thresholds, either auto-suggested or custom ones. It then automatically generates interactive Databricks SQL dashboards to visualize metric trends over time, making it easy to spot issues. You can set up SQL alerts to get notified via email or Slack if thresholds are breached. And there's the Databricks Assistant, the AI tool, which can actually help you write the SQL for your custom metrics based on natural language. Pretty handy.
AI help for custom monitoring. Nice.
Yeah.
Okay, quick mention of infrastructure as code, IAC. Why is managing infrastructure via code important for MLOps?
IAC is about defining and managing your infrastructure, compute, storage, networks, using configuration files, code, instead of clicking around manually. Huge benefits for MLOps. Lets you create consistent, repeatable environments, dev, staging, prod on demand. You can version control your infrastructure code in Git, track changes, easily roll back. Changes go through standard code reviews, pull requests, better collaboration, fewer errors. And it integrates perfectly with CI/CD pipelines, so you can automate provisioning your entire ML environment along with your code and models.
Bringing software dev best practices to infrastructure management. Right. Now let's make this really concrete. Let's look at some practical examples from those practice tests. First one, sales forecasting. The suggestion is batch deployment is often ideal. Why is that?
Well, for sales forecasting, you usually don't need predictions second by second, right? Forecasts are typically generated periodically, daily, weekly, maybe monthly for planning things like inventory. The input data, historical sales, seasonality, marketing plans, economic factors doesn't change instantly either. So processing this data in batches at set times to generate forecasts is usually efficient and totally sufficient for the business need. A real-time system would likely be overkill and might not add much value here. It's a classic batch use case.
The prediction cadence and data nature drive the deployment choice. Okay, another example, ML flow tracking in Python. What's the right way to log params, metrics, models?
Yeah, the best practice is using with mlflow.startrun.block. That context manager makes sure everything logged belongs to that specific run. Inside the block, mlflow.logparam for hyperparameters or configs.mlflow.logmetric for things like accuracy or loss. And then crucially, use the framework specific mlflow.flavor.logModel function. So mlflow.sclearn.logModel for scikit-learn, mlflow.pytorch.logModel for pytorch, etc. Don't just save the model file generically. Use logModel so MLCO gets all the metadata and registry integration. Forgetting the with block or using the wrong log model are common mistakes.
Start run, log specific things, use the right flavor log model.
Got it. Now, feature drift. The source says monitoring input feature distributions directly is better than just watching model coefficients change.
Why?
Right. While coefficient changes might hint at drift, they're also affected by complex interactions the model learned. A change could be for many reasons. Directly monitoring the stats of the input features themselves mean variance. The shape of the distribution gives you a much clearer, more direct signal that the incoming data is changing compared to the training data. It's generally earlier, more accurate detection of feature drift itself, separate from the model's internal dynamics.
A more direct, less noisy signal.
Okay.
What about label drift? What is it, and how do we usually tackle it based on the practice tests?
Label drift is when the distribution of the target variable, what you're trying to predict, changes in production compared to training. Like in that example where the proportion of churned customers suddenly increased. To fix it, first investigate why it changed. Review the labeling process. Is it still consistent? Accurate? If the real-world phenomenon changed or the labeling rules did, your old model might just be wrong now. Usually the fix is to retrain the model on more recent data that reflects the new label distribution and any updated labeling logic.
A shift in the target itself requires reviewing labeling and probably retraining.
Okay.
Real-time predictions often need just-in-time JIT feature collection using event-driven pipelines. Why is that critical?
For many real-time cases, like fraud detection, the absolute latest info is key. A batch pipeline updating features hourly might miss critical recent activity. An event-driven, real-time pipeline reacts instantly to events: a new transaction, a user click. It fetches the most current feature values from various sources right when the prediction is needed. This JIT collection ensures the model uses the freshest, most relevant data possible, which is vital for accuracy in dynamic, real-time situations.
Getting the freshest data precisely when needed makes sense. More technical one. Batch inference on a partitioned delta table. How do we make Spark use the partitions efficiently?
The key is simple. Put a filter in your query that uses the partition key column. When Spark sees where partition key accrues some value, it does partition pruning automatically. It only reads the data in the partitions that match the filter, skipping everything else. Massive performance boost, less data scanned, lower cost. So if it's partitioned by date, use where date, YYYYYMMDD. Don't filter, then repartition. That kills the benefit.
Filter directly on the partition key. Got it. MLflow model registry stages. What are the standard ones?
Typically, you see none, initial state, staging, ready for pre-prod testing, production, validated, serving live traffic, and archived, retired, but kept for records. The counterflow is none, Zilla, staging, copy, production, archived.
Core progression. The PyFunc flavor in MLflow, its main advantage is consistent pre-processing. How does it achieve that?
PyFunc lets you package the model and any custom Python code for pre-processing and maybe post-processing together. You define the pre-processing steps inside the PyFunc model's predict method, or related methods. This means the exact same transformations applied during training get applied at inference time, no matter where you serve the model locally, Databricks, somewhere else entirely. That consistency is critical. Mismatched pre-processing is a common cause of production model failure.
Encapsulating pre-processing with the model ensures consistency everywhere. Job clusters versus all-purpose clusters in Databricks. What's the main benefit of job clusters for production ML?
Cost savings, primarily. Job clusters are ephemeral. They automatically terminate when the job finishes. You only pay for compute when the job is actually running. All-purpose clusters can sit idle, costing money. For scheduled production jobs, a job cluster spins up, does the work, shuts down. Efficient. Plus, you can configure them with the exact libraries needed for that specific job, ensuring reproducibility.
Spin up, run, shut down. Cost-effective for scheduled tasks. A/B testing, again, what's a recommended strategy for deploying a new model for testing?
The standard approach is to deploy the new model B to a random subset of live users' traffic. The rest get the old model A, ensure the split is random and the groups are comparable. Then monitor key business metrics for both groups over a significant period. This lets you directly compare A vs B on live traffic in real conditions. Gives you solid data to decide whether to fully launch Model B.
Concurrent runs on live data for direct comparison. E2E tests and CI/CD. Why are they so good for ensuring model robustness?
Because they test the entire integrated system end-to-end, mimicking real usage. They feed representative input, run through pre-processing, get predictions, check outputs and side effects. This holistic view catches subtle integration issues, data format problems, environment quirks that unit or integration tests might miss. Gives high confidence the model will work reliably in production.
Testing the whole workflow like a real user. Delta time travel. How does it enable version control and retrieving old data?
Every change to a Delta table creates a new version. Delta time travel keeps a history of these versions. You can query the table as it was at a specific version number or timestamp. Select from my editable version as of 123. Super useful for reproducing old experiments with the exact same data, comparing model performance on different data snapshots, or even rolling back accidental changes using restore.
Going back in time for reproducibility and recovery. Chi-square test for categorical drift. Why is it suitable?
The chi-square test specifically compares observed category frequencies against expected frequencies. It tells you if the difference in distributions between, say, training data and current production data for a categorical feature is statistically significant. A significant result suggests the distribution has drifted.
Statistical check for changes in category proportions. Last one. Model registry webhooks for automation. How would you set one up to trigger batch inference when a model hits production?
You'd create a webhook in the model registry. Set the trigger event to model version transition stage. Add a filter so it only fires when the toastage is production. Then configure the action, usually providing a URL endpoint that the webhook will call. That endpoint would belong to a service you build that listens for the webhook notification and then kicks off the Databricks batch inference job, maybe passing the model name and version from the webhook payload. It automates that handoff.
Automating downstream tasks based on model stage. Very neat. Well, this has been an incredibly detailed and really insightful deep dive into machine learning operations. We've covered a huge amount. Fundamentals, components, practical steps, Databricks tools.
Yeah, quite a journey. We've seen how MLOps gives structure and automation to the whole ML lifecycle, emphasizing treating ML as code and data, leveraging CI/CD, robust testing, and hopefully those practical examples from the exam perspective really help connect the concepts to real-world application and what you might encounter.
Absolutely. So the big question for you, the listener, to chew on is this. How will implementing a really solid MLOps strategy not only streamline your day-to-day ML work, but also ensure the long-term reliability, the maintainability, and ultimately the real business value of your models in these dynamic, changing real-world scenarios? That's definitely something worth thinking about. We really encourage you to dig into the Databricks documentation further, keep practicing, and solidify these crucial concepts. Thank you so much for joining us on this deep dive. We look forward to our next exploration.